Hello everyone, my name is Claire Baffaut. I am a research hydrologist in Columbia, Missouri, and I am going to present Components 3. Components 3 addresses the need to quantify the benefits that conservation practices provide so that Congress and taxpayers can evaluate those benefits against the dollars that are invested in those practices. Components 3 focuses on 4 problem areas: the selection and placement of practices to achieve the most benefits, the development of more effective conservation practices, the linkage between conservation practices and profitability under a changing climate, and the linkage between conservation practices and ecosystem response. The first problem area is understanding how to select, place, and combine conservation practices to achieve improvements in water quantity and quality in watersheds. ARS has many notable accomplishments in this area. They improve our knowledge of nutrient management planning, of conservation practice placement. They help develop management plans, watershed management plans, and they improve our understanding of erosion processes and irrigation groundwater dynamics. This first accomplishment responds to the need for refined models that better predict the environmental benefits of USDA conservation program. This is a continuation of an effort that started 15 years ago when the Conservation Effect and Assessment Project, or CEAP, was beginning. CEAP is a multi-agency effort to evaluate and guide USDA conservation policy for wildlife, rangeland, and cropland. ARS, NRCS, and Texas A&M scientists in Temple, Texas, developed a system of models to predict the effectiveness of past and future USDA conservation policies on cropland. A second-generation CEAP modeling framework is under development and includes improved models, continuous US coverage, simulation of individual streams and fields, with crop rotation and management derived from remote sensing and survey data. It is informed by results and data from the long-term agroecosystem research network. So for example, the bottom left graphic describes predicted nitrogen reduction associated with 4 potential USDA conservation policies. Each policy comes with a differing level of expenses and has different treatment levels. This framework can operate at the national scales all the way down to an area within a field, as shown on the bottom right. Another research need was to develop models to understand how aquatic ecosystems or physical habitats respond to changes in agricultural watersheds resulting from conservation practices. This work is related to the previously mentioned CEAP modeling work. But whereas CEAP utilizes proprietary USDA producer survey data that cannot be easily shared, the National Agroecosystem Model uses only public data. This facilitates collaboration with multiple organizations and make it possible to link with other models that assess ecology or economics, for example. NAM uses a new SWOT Plus model and assesses a variety of environmental issues. The NAM system has a national extent and also operates at the field level, meaning that each field is a discrete computational unit. So for example, the figure on the left is the Goodwater Creek watershed. This is an LTAR watershed in central Missouri. You can see the individual fields in the watershed and the stream segments, and the color defines the level of runoff, high, medium, or low, predicted by the model. One of the products derived from NAM at the request of NRCS is the Agricultural Operation Planning Tool, AGOPT. AGOPT aids producers in scheduling the application of agrochemicals. It uses National Weather Service precipitation forecasts and automatically runs each day to predict which counties may have significant runoff in the next 3 days. and thus the producers can query AgOpt and decide whether to apply or not depending on that risk of runoff. Another research need was to identify cropland vulnerability to contaminant loss in support of developing strategies that optimize both production and environmental endpoints for agriculture. NRCS developed an index to do just that, classify cropland vulnerability to erosion and losses of agricultural input via runoff or leaching. It is called the Soil Vulnerability Index and is based on Surgo soil properties. NRCS goal is to include this index as one of the tools used to streamline assessment and delivery of conservation needs everywhere in the nation. This accomplishment is also in cooperation with SEEP. ARS scientists in Columbia, Missouri evaluated the SVI at 13 ARS SEEP watersheds across the United States. So for example, on the left you have the SVI map for one component of SVI for the Upper Snake Rock watershed in Idaho. So shown in red is the cropland with the most vulnerability, and in green the cropland with low vulnerability. White areas are not cropland. And to the right of that is Cedar Creek watershed in Indiana, the map for the same component of SVI, the runoff component. The finding of the studies across the 13 watershed include strengths and limitations, and those alert planners on when they can have confidence with SVI ranking and when they should be careful with it. An outcome of this is a request from NRCS to ARS to explore adding factors in SVI that relate to the rainfall amount and intensity and to the presence of a restrictive layer in the soil profile, and those were two of the weaknesses identified during the study. The second problem area was improving conservation technologies to better protect water resources and the development and testing of new designs, equipment, and materials. As for the previous problem area, a lot of work was accomplished in this area, and that led to improved understanding of the effect of practices such as reduced tillage and cover crop, and the development of new conservation technologies such as alum treatment, phosphorus recovery system, and a bioreactor to remove nitrate from water. All those protect water resources. As an example, I will talk about the development, testing, and evaluation of a precision agricultural system that combines well-known and novel practices. On claypan soils, which have a restrictive layer that impedes infiltration and increases runoff, there is a trade-off between erosion control and transport of dissolved pollutants. And because of that, no-till reduces erosion and sediment losses, but it can double or triple losses of pesticides such as atrazine and losses of dissolved phosphorus, as shown on the graph on the right. Scientists in Columbia, Missouri have shown with model simulation studies and long-term surface runoff monitoring that when no-till was combined with cover crops and a precision agricultural system, these losses, atrazine and dissolved phosphorus, were similar to those in the baseline system, which was a minimum till system. Crop yields were maintained as well. On these soils, combining multiple practices was necessary and successful to avoid trade-offs between erosion and the transport of dissolved pollutants. The third problem area is to ensure that conservation and agricultural management practices can increase agricultural profitability and resilience under changing climate and land use. Our research need in this area was the optimization of practices to accommodate a broad range of climate conditions. The majority of climate change studies are based on the output of climate change models, which are then downscaled to the study area to produce daily precipitation and temperature time series. Those are in turn fed into computer simulation models that evaluate production, profitability, and environmental performance of agricultural systems. One challenge with the time series produced by climate change models is that large events often do not exceed the largest event observed during the historical period. Several efforts within ARS have addressed this challenge. The solutions developed by scientists in El Reno, Oklahoma, uses Syntor. Syntor can generate a synthetic daily precipitation time series based on the precipitation occurrence distribution. For extreme storms, let's say the top 10 percentile, one can adjust the precipitation distribution based on a prescribed percent change or according to the percent shift projected by the regional climate model. So for example, on the top right, you have the blue line, which is the precipitation distribution predicted by the climate change models. And then to the right of that, a shift is applied to different percentiles depending on what the scientist decides. Then there is a smoothing of the resulting curve on the bottom right. And then based on this newly adjusted precipitation probability distribution, Syntor can generate a daily time series of precipitation representative of future precipitation sequence of extreme events. This series will then be used to simulate climate impacts using crop and hydrological models. Another research need aims to improve our understanding of how crops will respond to uncertain changes. This modeling study addresses crop selection and planting timing in the southern high plains, a region characterized by uncertain rainfall. Typically, rain amounts during the growing season are uncertain, which makes dry land production challenging. However, the Ogallala aquifer depletion may increase a fraction of dryland production. Scientists in Bushland, Texas have used crop models to simulate cotton and sorghum yields at multiple locations in the cotton sorghum area of the Panhandle for multiple planting dates. When combined with prices producers can expect to get for the crops, the resulting yields are used to estimate the risk of making or losing money depending on the starting date. Thus, one can determine an optimal planting date for each crop or decide what crop to plant at a given date for maximum profit. The model results confirm conventional practices in this area and put numbers behind them, which can be used for developing management tools or for the analysis of the effect of a changing climate. The scientists do have plans to develop a web application that compares the economics of dryland cotton and sorghum production based on user-specified commodity prices and production costs. The fourth problem area is about the link between conservation practice and ecosystem response across agricultural landscape and aquatic system. This is an emerging effort within ARS, and the first step was to collect data and develop models to understand how aquatic ecosystem or physical habitats respond to restoration practices. For western grazing land, fire and invasive species threaten continued access to grazing resources. So there is a need to understand the landscape and climate factors that affect the success of seeding treatments after fire. Scientists in Fort Collins, Colorado, used field data combined with remotely sensed data sets and gridded climate data to develop a predictive model that identifies where seeding and restoration efforts will be most successful. They used the data obtained following the 2015 soda fire in Idaho and Oregon, and developed and used an artificial intelligence framework to complete two objectives. The first one is to understand the trade-offs between sagebrush and other vegetation that grows after fire. Sagebrush is used as an indicator of a healthy ecosystem that will include many grazable perennial grass species. The relationships between sagebrush and other vegetation are shown on the bottom left graph. All the way to the left shows that annual grasses are detrimental to sagebrush recovery. In the middle, we see that perennial grasses need to be balanced with sagebrush for optimal sagebrush recovery. And on the right, we see that fertile island cover, which is a cover typical of areas that had sagebrush before it burned, is a good predictor of sagebrush recovery. The second objective was to identify key predictors of successful sagebrush recovery and narrow down where restoration efforts are likely to be most successful. The results were used to develop maps of sagebrush recovery probability after using treatment, meaning after seeding. The Bureau of Land Management and the state of Idaho have used those findings to modify and plan seeding efforts in reburn areas of the Soda Fire in 2017 and 2019. And that concludes my presentation of Components 3.